Can everyone see the screen? Also good. Okay, perfect.
Yes.
So it's my pleasure to teach you Aeroacoustics this semester. It's a joint course. It will be taught by me and Professor Kaltenbacher. And it's separated in a lecture where you are in now and a practical course. In the practical course, we do calculations for the aeroacoustics itself and do a little bit of getting a grip on measurement technologies and what's aeroacoustic simulations about, so that you get a first impression. Please also use the chat if you have any questions during the lecture. Probably I will cover it, probably at the end of the lecture, or if I see it in between, or if you just jump in with the question, I will cover it right now. So yeah, aeroacoustics. Before we start with the lecture, I will briefly introduce our institute. I think most of you know it well. I saw most of you are all also electrical engineers. Is that true? So yeah, all electrical engineers know people from other studies. Because I think then I will tune the level of fluid dynamics and acoustics itself to your needs, that you get the basics and what it is about, so that we really have a common basis on that. So what's the institute about? You all know it. We have a new institute head. It's Manfred Kaltenbacher. He came from Vienna, as I did. I also come from the TU Wien. And years before, we also had the lecture Aeroacoustics in Vienna, which will now be taught at the TU Graz. And I'm very happy that I have so many participants, because I think it's especially important for electrical engineers to get a grip on aeroacoustics or acoustics and NVH topics itself, because electrification of cars is pushing forward, and you don't have this masking engine noise anymore, and it will be play a dominant role for the new or for the car manufacturers in the future to deal with this topic. But I will show you later within some research project we're doing. Okay, so that's the
I would like to point out that most of us are not electrical engineers, but actually audio engineers.
Okay,
so,
even better.
We come from the audio domain rather than
Okay.
the electrical domain.
Okay, perfect. So I guess you're familiar with the wave equation itself and stuff like that.
Yes.
Yeah, and fluid dynamics will be a little bit of new stuff for you.
I guess, yeah.
Okay, perfect. To jump right into the fluid dynamics topic, I have also on my YouTube channel the basics covered there. So I will encourage you to watch the videos until next week. So they cover all the basics, and then we can repeat it during the lecture. Okay, nice. Okay, this also means that most of you don't know the institute very well, or
I think we all had the fundamentals of electrical engineering and
dynamics. The course is here?
Yeah.
Yeah, okay. So, okay, you all had it probably in the bachelor and in the master's, we provide some additional background in multi-physical systems, modeling and simulations, like here, kind of a injection valve where we tuned or reduced the injection time by using piezoelectric materials. Then at the institute, we also do courses on optimization. So probably if you're interested in that, have a look at them. And of course, the section Vibro and Aeroacoustics, where you are now in. And there is the lecture and the practical course Aeroacoustics. Okay, that was teaching. About research, what I do at the institute is we have a software which is called openCFS. It's a finite element software where we can model different physical fields. For instance, the electrodynamical field, mechanical field, acoustical field, heat, flow, and we can incorporate different solvers from other companies into our system to couple all these systems together. Okay, so therefore we do in the research, we do modeling, we do simulations, we do optimizations. We also do measuring, validation, and characterization of materials. So we more or less cover the whole domain of product development, or as it now called, virtual twin stuff. And that's basically what we do in all or the listed physical fields. So as I said before, we can compute single fields itself, so just concentrating on electrodynamics or mechanics or acoustics, heat or flow. We can also couple specific fields, like we can do piezoelectrical computations, as I said you before, with the injection valve. Then we also are capable of doing or coupling electrostatic mechanics and acoustics. For instance, we did projects on MEMS loudspeakers where we simulated them. And there we also incorporated somehow the piezoelectricity there. The software is capable of coupling mechanics, magnetics, and acoustics. So the typical application is if you have a transformer that it emits some noise, and how to go from the excitation itself, from the magnetics to the acoustics. It's all covered within the software. Then we have the coupling between magnetics and heat. For instance, when you kind of anneal sheet material or stuff like that, you often use induction heating, and this induction heating process can be modeled within the software. And last but not least, it's probably why you are here. We can model flow-induced sound. Flow-induced sound and also covering vibroacoustics is a very important topic, as I said, for the electrification of cars, and also for cooling of batteries and stuff like that. And here you see a kind of cooling fan, which is rotating at a specific speed, and there we do flow simulations, and from the flow simulations we connect it to our simulation solver and then compute out the acoustics. And you will now learn the basics on how to do that, the models that we are dealing with. And that's what the course is about, to get the foundation to be able to do such simulations and measurements. Okay. And we're also doing currently a project with industry partners and research institutions and funders. First of all, we have project with the classical car manufacturer like BMW. There we do optimization of the noise characteristics of turbochargers. We also tune the characteristics of the whole car body itself. So like car frame noise and NVH topics like noise, vibration, and harshness is a big topic. And yeah, the third project with Rafael List, it's flow noise in e-mobiles. A little bit funny name, but therefore it's all about flow within flow in pipes, and it's more about fuel cells and what type of noises are occurring in the pipes in fuel cells. And then a very interesting topic, probably also for you as audio engineers, is the human phonation. The way and how I can speak to you is a pure aeroacoustic phenomena, and we are investigating in a big project this, and also there we cover new approaches for doctors to get towards a new treatment in hospitals. And yeah, it's very interesting. Yeah, it's a relation, or it relates engineering and medicine. And yeah, in the future we will do there some cancer studies when the vocal folds, which are oscillating, are kind of have some of these polyps on it, and how they act during their voice production. Okay, and the other projects I will not name now. And of course, as we are doing projects with industry partners, we are searching for students working with us. And yeah, but we can discuss this later, or just send me an email if you're interested in some of the projects and you want to do some bachelor, master thesis, or just work at our institute. Okay, that was all about the current project. If you would like to go in depth for some specific project, we can do this now. So any suggestions I have available a little bit on HVAC topics like cooling of battery systems, then how we mitigate noise there, then NVH topics at car frame noise, and then the turbocharger modeling and what we do there with the Aeroacoustics, some sound source localization, or human phonation. So you can select one, or if you just say go over all the topics, I will just cover all of them.
I would be interested in sound source localization. If you can do that in more detail, maybe.
Yeah. Okay. Okay. Probably I will start at the HVAC system, and here we can see some mechanisms that produce sound, and then go to the sound source localization, because then you have some detailed background about what type of flow structures produce sound, and then we can interpret it a little bit better. Okay, the HVAC system topic is HVAC means heating, ventilation, and air conditioning and cooling systems. With increasing electrifications in the cars and electric drive systems, we have a high demand on cooling during the charging. This means it is not before in the classical engines when we had high speeds and high accelerations of the car, we had a high demand on cooling. Now in the electrical car system, we have the high demand on cooling during the charging and decharging of the battery. When we decharge the battery, probably the car is moving, so other sound sources are masking the fans and the cooling systems, but we charge the cars when the car is kind of standing in the parking slot, and therefore we have, when the car is located in front of your house, we have a high demand of cooling, and this high demand of cooling results in a high noise emission. And this is not fun, because if you're probably living in a nice street and it's all very quiet and you probably hear the birds and stuff like that, and then some car is charging and you have a big fan cooling the battery, it's probably not so cool. Therefore, we investigate how to reduce the sound sources, but first we have to identify the sound sources. And as you see here this is a chart of the flow speed and some illustration of the vorticity structures that the fan is producing. So during the rotation of the fan, it produces vortical structures, and these vortical structures then result in accelerations of the fluid, or are consequences of the accelerations in the fluid. And these accelerations connected to vortical structures are flow-induced sound sources. When these structures then hit another structure, so for instance, here you have the blade of the rotor. Can you see the cursor? Okay, perfect. Here you have the blade of the rotor. There are vortical structures developing and traveling in the duct. And then these vertical structures probably also hit the electrical motor back to in the backflow, and then interact with the structure. It even emits more sound, and then with our sound models of flow-induced sound, we can then calculate the acoustics. So here, then you imagine the waves are traveling upstreams and downstreams, and you can hear these waves. You cannot hear the fluid dynamics per se, but you then hear the byproduct and the little energy which is transformed by the waves to your ear. And the question is now, how can we also locate them with microphones, as you're interested in sound source localization? When we do sound source localization for this particular fan, for instance, we place here microphones in front of duct. For the specific topic of rotating structures, we have to use a ring array, but you will learn it throughout the course. And now we can go to the sound source localization. Maybe to get an impression on the setting of this project, it was a cooperation with Mercedes-Benz, and we used a typical microphone array setting. So in front of the car and on the top of the ceiling of the wind tunnel, we mounted microphones, a lot of them. I think it was nearly between 100 and 200 microphones. And at each microphone position, we recorded all the incoming sound, and then at specific frequency, we could deconvolute these sound signals and identify the sources. And here you see the sources in the front of the car there. The sources are probably there because there is a kind of an edge in the car body where the flow is accelerated into these directions to move along the side of the car and through the bottom of the car. And also there are sources close to the side mirror, and at this specific frequency, I don't know what it was exactly, but there are the main sound sources. And we will cover how to do sound source localization in the third chapter of the course. It's about the measurement technology. Have you any specific questions on that?
Yeah, I would have a question. When you do these measurements, how you distinguish between the actual flow? I mean, it was mounted in a tunnel. Is that right?
Yeah.
Yeah. So how distinguish between the actual flow and the sound wave that are produced by the flow? I could imagine that it's pretty hard. Do you it by selecting specific frequencies, or do you some more fancy stuff?
Yeah, the fancy stuff there was that we used the free field Green's function of the wave radiation,
Yeah.
and therefore we get somehow disconnected the flow with the acoustics.
Okay, and you do it afterwards via
Yeah, that's
post-processing of the signals.
Yeah, that's purely signal processing.
Okay.
That's very specific for that. But as you pointed out, it is a big challenge to measure in when you have flow.
Yeah. So is a flow actually a more low frequent phenomena, or are there also high components when there aren't any objects where the flow is, don't know, broken or yeah.
It really depends on the setting. For instance, like music instruments, most of them are flow-induced sound, and you can either have a very tonal characteristics,
Yeah.
or you can have really kind of a broadband setting of different type of noise sources produced by fluctuations, which are then mostly turbulent fluctuations. For instance, here at this fan setting, you have a strong broadband characteristics from the unsteady interaction from the blades and the inbrought turbulence by the flow. So maybe you have heard it at some point in your life that when you have a flow, then it has a certain content of turbulence.
Mm-hmm.
And this certain content of turbulence then interacts with the blades and generates at the blade tips a tonal component which is called a blade passing frequency.
Yeah.
And on the other side, it also makes kind of the turbulent noise, which is more random and broadband over the whole frequency
Okay.
range.
Mm-hmm.
So this turbulent and vertical structures kind of flowing through the duct and are cut by the fan are then resulting in the tonal component and also in the broadband component.
Okay.
Yeah, and usually all noise sources related to turbulence are more broadband. Noise sources related to discrete vertical structures like whistling. Whistling is a special phenomena where you have kind of a jet which is impinging on a cutting edge.
Mm-hmm.
So you have kind of a jet flowing there, and my other thing is probably not a cutting edge, and on this cutting edge the flow is then divided, and a special feedback mechanism which is covered in the lecture notes in the applications section is then triggering a very tonal component. Probably I can show you that. So that is the lecture note.
Mm-hmm.
And in the application section, we have a section which is called cavity tones. And this is very specific and somehow related to your question, how to distinguish between broadband components and tonal components. And there are things like this shear layer mode here is a very specific mode where kind of the shear layer gets unstable over the cavity and then probably forms some vortices, and these vortices are then clipped by the trailing edge, and this emits a very tonal component,
Mm-hmm.
which is used at within typical music instruments which would like to have a very discrete tone.
Yeah.
Yeah.
Thank you.
So have a look at that and you will get more thing there. Okay. Any other project we should discuss now? But
Yeah, I would be very interested in the human phonation project.
Yeah,
if that's possible.
Yeah, of course. The human phonation project. So the biomedical setting is we have the lungs, and between the mouth and the lungs there is the larynx where the vocal folds are. The vocal folds are this, it's called here vibrating solid. These are the folds here. So we have the vocal folds and then we have the false vocal folds. The vocal folds are the vibrating ones, the false vocal folds are just there to stabilize the flow. And then you can speak more efficiently. So it's a kind of a flow treatment, because probably you have heard it at some point that it's called Coanda effect. If you have a jet through a small hole and then walls around this jet, then the jet will kind of touch towards one wall, and the false vocal folds prevent this flow of doing the Coanda effect, and so can speak more efficiently. Okay, so the whole setting is the vocal folds are vibrating due to the airstream which are you pressing through the lungs throughout your mouth. These vocal folds are then vibrating around between 100 and 300 hertz, depending on your age and sex and so on. And then these vocal folds are kind of oscillating or vibrating, and at each vibration they cut the flowchat. And during the cutting of the flowchat, we produce at each cycle sound sources, and these sound sources are then modulated by the vocal tract. The vocal tract is more or less the oral, nasal, and the whole tract throughout the mouth, and it is very special for different vocals. Like when you do a ah, you kind of articulate differently as you do for a e, and this is very characteristic. And there are also some special models we are introducing into the whole project, which is called SimVoice, and this project aims to detect what are the sound sources with respect to the aeroacoustic formulation. And this is just the engineering goal. The ultimate goal of this project is to get special treatments for people having some problems with their voice, like the politician Doskozil. And this model SimVoice is should be used in the future to predict surgical treatment. So in the sense when some doctors are planning, for instance, Doskozil's new voice, then they are cutting with kind of their knives, small in the top of the vocal folds. They're kind of introducing some, from an engineering point of view, some stiffness through some special treatment, and then we can predict with this model how this works. So that's the aim of the project, and we are now in the half time or half period, and it's very interesting. We learn a lot of things. Also very interesting to work with people with different mindsets from other disciplines. Yeah.
Can I ask a follow-up question?
Yeah, of course.
Because last year at the Interspeech conference in Graz, there was presented a similar project, which was a finite element simulation of the vocal tract. And I don't know if I understood you correctly, but I think you do simulation of the vocal tract by simulating different sound sources. Can you make a prediction which method is faster? The method of simulating the whole vocal tract with its physical properties, or I guess you could say the material properties, or by focusing on the sound sources themselves. Which one would be faster in terms of computation time?
It would definitely be faster, not considering the material properties of the vocal tract, because if you consider them, you either have to incorporate it into your acoustical model, or you have to simulate also the mechanics or mechanical PD with the finite element. model. So if you incorporate the model into the acoustical PDE by some fancy impedance boundary condition, that's good, and it's fast. But if you're also computing the mechanical properties within your finite element method, then it will, be slower. I don't know how much slower, but it will be definitely slower. Probably to get an impression of what we are doing, in the practical course, I will present in detail the human phonation project. There we kind of go through it. We kind of have here a small section where we compute our sound sources from flow simulations. Then we have some boundary conditions towards the lungs, which are emulating the behavior of the lungs. Then we have an interface towards the vocal tract, which is kind of this purple shape here. Here it's just a straight pipe because we would like to validate our model with the measurements we had done before. And then here the other interface there towards the kind of cube there is the opening of the mouth. And so the sound sources are produced and applied here on the wave equation, and then they are propagating out there and into the far field. And this is all done with the acoustic propagation, all done with finite elements. Yeah. And the flow simulation is done with star CCM, a finite volume solver in 3D. Yeah. Good. Did that answer your question?
Yes, thank you.
Okay. Anything more on projects?
Can I ask another question?
Yeah, of course.
So in telecommunication or speech processing, we learned there you have these excitation and you have this filter, and more or less that's what is done in these modern communication systems. And my question is related. Do we need a FEM simulation of the filter afterwards, after the excitation? So I would say, okay, excitation modeling with aeroacoustics does make sense. And afterwards, can we just assume a normal filter that is that simulates the part of the vocal tract? Is this enough, or why we have to do such FEM simulations?
Yeah, that's correct. We could use just a filter there.
Mm-hmm.
We are also planning in the future to just replace the purple pipe,
Mm-hmm.
which is then kind of some shape of your vocal tract
Mm-hmm.
by a simple equation model that does the filtering. So yeah, that's a common approach we can use. So you don't have to really resolve the whole vocal tract.
Mm-hmm.
But on the other side, the SimVoice project would like to develop into the direction that we then use MRI scans of the patient to kind of really have their geometry and then kind of discretize this to have really a personalized model of their voice and stuff like this.
Okay.
So yeah, that's the goal of the project. But if you would just model voice as you wish to do, that's okay and reasonable.
So is it more accurate do it by FEM? So what are the gains of the FEM simulation?
The gain is that we in the next step we can introduce more geometrical model complexity. That's
Okay.
that's the only gain. But if you have measurements from the transfer function from the vocal folds where the sound sources are to in front of your mouth, then it's also fine. But yeah, often there are not the measurements available, and not every person would like to have something put that deep into his mouth.
Okay.
Yeah. Probably sounds a little bit funny, just cutting that out of the video. Okay. Yeah. Any other question? Okay, then we probably start with what we learn in the course, and then a little bit about the examination, and I think afterwards we then have some time for additional questions, and then we call the lecture day, and we afterwards proceed with the exercises. Okay, so the Aeroacoustics course content will be about flow-induced sound, and it's called Aeroacoustics, and it's somehow related. We will learn what type of noises can we expect when a car is driving, when we do some energy harvesting and have rotating geometries. Then we also can interpret with these models how typical musical instruments work, and we have here a chat. Anyone knows why we probably consider this fighter jet? Probably not. The first idea of Lighthill was to investigate jet noise, and there the exit jet of this engine of a typical fighter jet, and it was right after the Second World War, and the idea was to reduce the noise characteristics of stuff like this. There's also the idea that we can differentiate between sound and noise. Noise not in terms of measurement noise, but noise is kind of the bad sound, and sound is creates desire, and noise creates headaches, and we would like to produce better sound quality and reduce the noise in order to reduce the stress on the people's mind. It is proven that when we increase the noise in the surrounding of a person than the concentration lacks. And therefore it is also important to look at these topics. Again, it was the original, the first idea to reduce the noise sources of kind of jets like this. And we will learn the tools how to reduce them, and accordingly also for the other applications. And we would like to hide the jet. So you can be probably a military enthusiast, what we are probably not in Austria, but a lot of the Americans are, and the biggest conferences are, and they are speaking a lot of stealth technology is not only about the radar signature, but also on the sound signature. And we would like to make the picture like a blue sky and no plane in the noise sense. So this is what we will learn. We will learn throughout the course, that we can identify the noise sources, and we have then the steering wheel to reduce the noise sources there. The big scientific challenge is that noise is more or less flow-induced sound is more or less a byproduct of some flow. The flow is typically used to drive some energy, and reducing the energy of the flow does not correlate well with the noise emissions. And this is kind of a big challenge. And also there is a challenge of the disparity of scales. Hearing, as we discussed before, and the relation to turbulence. Turbulence is more or less a broadband characteristics spanning over a whole range of frequencies, and at some parts of the frequency we have the ability to hear. Converting these frequencies into length scales, the flow scale, the frequency scales different into length as acoustics does. Acoustic, the frequency and the length scale is related with the speed of sound, and the turbulence not. Therefore, the two mechanisms kind of are drifting apart of each other, and this means with respect to simulations that we have to treat, or we should treat turbulence differently than acoustics. So discretizing a small turbulence structure is different from discretizing a wave, or modeling a wave, or measuring a wave. Just imagine again a jet or an airplane traveling above you. You will don't flee it. You will not kind of experience the turbulence that the airplane is producing, but you will hear it, even kilometers away. And that's pretty big challenge. That's the same for the pressure as a synonym for the energy. The energy in the acoustical spectrum is very low, but the driving force of the flow is very high. And so often people in research would like to model acoustics and flow within one simulation and treat it as one. Because physically, the pressure is the pressure, and the pressure has some acoustical content in it, but it also has the flow content in it. So we have an overall pressure, and their philosophy is that we kind of treat it with one simulation, but this simulation must be very accurate for a wide range of scales, because often this driving flow has pressures, I don't know, 100 kilopascals or stuff like that, and then the hearing is some milli or micropascals, and then you have a very long number, and probably the last digits, which are more or less round-off errors, you can hear them already. That's not good. So that's a big challenge in the scientific community.
Excuse me?
Yeah.
Can you just explain a little bit why you differentiate at the length scale between hearing and the acoustic far field?
Yeah. Hearing was just expressed as it's more or less the organ, so where you hear, and the acoustic far field is how far acoustics travels. That was the only thing about differentiating there. Yep. Any other question?
So the length scale means the Abstand,
Yeah.
not the wavelength, but
just the distance. Yeah.
Okay, the distance.
Yeah. But it could also be the wavelength.
Okay.
So typically that at a turbulent scale, like name it L. L is and the acoustic wavelength, they are proportional by the inverse of the Mach number. As you increase or decrease the Mach number, the two scales drift apart. So if you have a turbulent eddy, it has a diameter of L, and when you divide it by the Mach number, you have more or less the acoustic wave which this eddy is emitting. And therefore, also for the simple eddy case, the two scales are quite different. Yeah.
Thank you.
Another question. Could we also differentiate in terms of velocities? So how flow velocity is related to acoustic velocity, or are there any relations, or how it's
yeah, it's very similar to the pressure.
Okay.
So as you just imagine that the velocity squared is some representation of energy, then you have more or less a similar relation as the pressure relation. Did I answer your question?
Yeah. Mm-hmm.
Okay. Perfect. Then I think I will go to the example we will kind of always refer back to. It's the flow around an obstacle. So if you just have a rod exposed to wind, then the obstacle is more or less an infinite cylinder where we have a flow around this infinite cylinder, and typically in the atmosphere we have low Mach number and also low Reynolds number. Here's the definition of the Reynolds number and the Mach number. Has everyone heard about from these two numbers, or are they new for you?
think the Reynolds is new for us. The Mach, at least we heard about.
Yeah. Okay. The Mach number is a dimensionless flow speed. This means the flow speed here with the small v is divided by the speed of sound, and Mach below 1 is subsonic, above 1 is supersonic, and then I think above 3 or so is hypersonic and so stuff like that. And yeah, very low Mach numbers are like if you have a flow which is driven by 10 meters per second, or yeah, a car is traveling with 100 kilometers per hour, it's about a Mach number of 0.1. So that's a typical range for a Mach number. The Reynolds number is a measure for how the relation is between inertial forces and viscous forces in the flow, and it describes more or less if you are in a viscous state or in a turbulent state. But we will learn that later on. Okay. Yeah, I will cover the Reynolds number and the Mach number in the next lectures, and there are also the definitions online in the YouTube videos. Okay, for this obstacle in the flow, we have a physical effect which is called the von Karman-Wozzeck street. It has a very typical shape and a very tonal sound results from this Karman-Wozzeck street. This Karman-Wozzeck street occurs typically in a flow range of Reynolds numbers about 200. And the resulting acoustics is a dipole shape here. Well, yeah. So here the flow is in this direction. I'm sorry that the picture of the acoustic radiation has the flow in this direction. But here you see clearly the dipole shape of the acoustic radiation. And we will refer back to this example throughout the lecture and also in the exercises. Any questions on that? Okay, good. Then throughout the lecture, we'll also cover a little bit about the experimental approach in aeroacoustics and how it is used, what are typical measures and measurement technology we are using, like the aeroacoustic wind tunnel, yeah, typical flow measurement systems, then microphone arrays, yeah, and sound probes and the wall pressure sensors. And then we will discuss a little bit the advantages of them and also disadvantages. And in connection to the experimental approach, we will also discuss the numerical approach about virtual prototyping and digital twin. The comparison of experimental approach and numerical approach will be covered in the exercises. Yeah, so I will leave it here like that. And now we come to the content of the course. We are first doing the fundamentals of fluid dynamics. As the understanding of fluid dynamics is crucial for the source mechanisms, then we do the fundamentals of acoustics, as most of you are already kind of specialists there. The acoustics is second because acoustics is the model of the wave transportation. So we plug in fluid dynamics and then propagate acoustics. And this is then convoluted in the aeroacoustics section, and then we have the experimental section. But yeah, probably we will shift the aeroacoustics and the experimental approach, but I'm not sure yet. And then we discuss some applications, but most of the applications are discussed in the exercise course of aeroacoustics here, stated here. And I think mostly all of you are in the exercises. Is this true? So a lot of head shaking. I guess that was agree. More details on fluid dynamics. Afterwards, after this section, you will be able to interpret aeroacoustic relevant equations, physical effects, and we will cover conservation equations, dimensionless numbers as the Mach and the Reynolds number we heard before, and Helmholtz decomposition will be taught by me. Then we, in the fundamentals of acoustics, we will discuss the acoustic wave equation, also dimensionless numbers, and yeah, some stuff on Green's function, how to propagate acoustics with an analytical model. And having these two fundamentals, then we go to the aeroacoustics, and there we learn how aeroacoustics model behave, and we discuss aeroacoustic analogies, perturbation equations, and some solution strategies. And then at the end, we will cover some validation and measurement technology for some specific tasks. And this will be more from the practical viewpoint. And then, yeah, of course, as I said before, we're doing in the exercise course a lot of applications and how you can transfer the knowledge into real calculations and even get some ideas of how to do a project and deliver results there. Yeah, that's basically the content of the course. The exam of the anything someone wants to add or discuss here? Okay, good. The homework or the exam will be split up into some homework part. At each chapter, you prepare some tasks, you submit them, then we will discuss them, and then we do a short oral examination, which will be very short, and we discuss more or less the homework you submitted. So it will be not that hard exam. I think it's fair for a master's course. Yeah, the exam or the hand-in assignments are more or less these examples, and here you have the dates when you have to hand them in. At the end of each chapter, so FD means fluid dynamics, A means acoustics, M means measurement technology, and AA means aeroacoustics. For each chapter you have to prepare four tasks, and we will discuss them at these two dates there. So one is this, the homework exercise 1 and 2 is discussed in December, and the homework exercise 3 and 4 is discussed at the end of January. The formatting will be, or the format of the submission will be the following. You do the calculation, handwritten. The reason is you will probably exchange knowledge with me and with your colleagues, and I would like to ensure that everyone has at least written his stuff itself. To every step during one example, I would like you to encourage to make a short note why you do this step, and then when you have done your examples, then scan them and just mail them to me. And that's basically the submission. I will grade your submission, and then we will discuss the submissions at these dates. Sounds good?
I have a question. Is this examination only now valid for the lecture or also for the exercises, or how is that related?
That's only for the lecture.
Okay.
During the exercises, we will execute different examples.
Okay. And for the exercises, only attendance is
Yeah, for the exercises only the exercise examples are counted. And
okay.
there is no final exam at the exercise course. And in the exercise course, we will only kind of rate the discussion and the submissions itself.
Okay.
Yeah. So
do I get it right? So for the exercises, there are also additional homework, or there's also additional homework to do.
Yes.
Okay.
So these hand-in assignments here in the lecture are more theoretical and more thinking itself. We can probably jump to one of these examples, like FD1 and 3. Here for instance is explain the difference between a Lorentzian and Lagrangian description of physical fields and provide at least three examples. This is not really calculation. This is just looking up in the lecture notes, and you will get it. Or just discussing it with me next week. So if you already know the questions, then you can ask throughout the lecture. So it really depends on you how much you ask during the lecture, and then probably you have already the answer to the questions. Because I myself will not look at the questions you before you hand them in, so I probably don't know what FD3 is. Yeah. So just a hint for you. Okay. Any further discussion on the examination? Nope. Okay. Then the lecture notes we provide is, first of all, the manuscript in the Teach Center. I think most of you were already in the Teach Center. There I have the outline of the course, the WebEx link there, the slides, we are doing today, then the lecture manuscript, then here the YouTube videos for next week. I would like to encourage you that you watch them before we start next week, because the basics in fluid dynamics will be kind of hard and tough. So yeah, have a look at them, and yeah, that's it. Then we have the 4 parts: fluid dynamics, acoustics, measurements, and acoustic analogies. And there we have always the slides, and here just the submission. As a reminder, yeah, you can submit it here or just mail it to me. So it's all good for the lecture notes, or do you have any questions? Good, perfect. Yeah, it's called lecture fun. Probably it's not. So the lecture will be a stream about or on WebEx. We will go over the slides, and yeah, of course I will answer your question right away. And yeah, questions. I would like to encourage you to ask questions, and also if you don't like to ask them via the microphone, just put it into the chat. I will answer them there. Genau. And the lecture stream videos will then be available, yeah, after a day, something like this. I don't know how long the WebEx system needs for the lecture record to share it. Okay, that's more or less all about the lecture. And yeah, any questions on that? Nope. Then yeah, of course, we have the possibility within our project that we can employ students and also do master thesis projects and stuff like that. If you're interested in things or graduation there, just write me an email. I'm happy for any student which would like to contribute to our research. So thanks. That was all for the lecture. Any questions? Any comments?
I have more or less a fundamental question, like
Yep.
In the fundamental acoustic courses, in some of them we heard that simulating acoustic fields is hard with finite element method, because you need very small elements to cover the hearing range of humans. And this was the explanation why finite element methods are not taught.
Not good.
Not good for acoustic simulation for the human perception. What is your viewpoint on that?
My viewpoint is probably a little bit diplomatic on that. It really depends on what mechanisms you would like to grasp. So if you would just simply propagate acoustics over a long distance from, I don't know, kind of a person is shouting on the one side of the field towards another person on a mountain, then probably ray tracing or stuff like that would be the method of choice. If you are investigating the mechanism, how the sound is generated in the near field and how it is generated in a more closer environment, then finite element is definitely valid and has the ability to incorporate different geometrical effects. But it's kind of in the contrast to what is acoustically compact, how can we defeature, what can we really reduce in the whole system we are investigating. So for instance, we are doing some specific probably I go to this slide there, some low frequency flow and vibrational induced sound simulations. There it's definitely valid and also preferable to use stuff like that, because you can incorporate the mechanical vibration and the geometry as it is. That's, maybe it sounds a little bit foolish, but that is why a finite element is so important for companies itself, because they can or they find their products in the simulation and not just an abstract way of doing it. So just from a more or less, let's say, marketing point of view, it's also more it gives you more basis for them to understand what you're doing. So in this sense, if physics matches in the low frequency range, it's definitely valid. I would not recommend using finite element, I don't know, in the 15 kilohertz range or stuff like that, because usually you would like to discretize a wavelength with using about 20 elements if they're linear. There are some special techniques like using spectral elements with very specific basis functions that are already incorporating like what is the shape of the wave. Then you can use an element per wavelength, is also possible, but it really depends on what you are actually doing and what's the assumption and the context you're using it for.
Okay, thank you.
Any other question on the lecture? No. To all attending the lecture, do you know anybody which is also attending the practical course apart from you? Because I checked the subscriptions and I didn't saw people or additional people signing up. Okay. Good.
Sorry, maybe just another question for myself. What is the difference of this course to the numerical simulation courses? Are the numerical simulation courses are more related to the other physical effects, or what is covered there?
Okay, I will go to the courses.
Just
To
to know.
Okay.
Yeah, to the multiphysical simulation.
Okay, the multiphysical simulation 2. This year it's called Simulation of Time-Dependent Field, the last time. And there we also cover a lot of magnetics and simulations there. And only a part of the multiphysical simulation 2 is simulating aeroacoustic fields.
Okay.
So it's more or less 40% is acoustics and aeroacoustics, and 60% is magnetics. And it's purely simulation. We will not discuss the models there, and we also don't discuss the physics there.
Okay.
So it's just simulation. Yesterday there was the first lecture, but if you would like to also go into this course, I can.
No, I just want to make sure that I am in the right course, more or less. That fits more to my interest.
Okay, yeah. So here we cover the physics and the models, and in the exercises we will kind of build the bridge towards computational acoustics. So that you get an impression about what it is, but you are not doing it.
Okay, thanks.
That's it. Okay. Then I think I will close this session and we go to the other WebEx meeting of the exercises. It should be that one.
Is there now a little break, or?
Yeah, we do a break about 15 minutes.
Okay.
Yeah, so we'll see us at 10:10. But I will open the other WebEx meeting already, that you can be in there, and then we start at 10:10. Okay.
Okay, thank you. See you.